I will start this class. This is class 6. Well, so from now we will change the topic. We have already closed the chapter of Lefschetz theorems. I have improved hard Lefschetz theorem, and but I will prove it later. So now, what I want to do is to pass to like another big subject in Hodge theory, that it's like the L2 part of Hodge theory. I mean, more analytic part of Hodge theory. And so, before doing that, I will spend this class into recall some facts from complex geometry. Okay. So this class is just recalling review of complex geometry. Okay. Okay. So, well. So for us, a complex manifold. So a complex manifold. Maybe this class will be too elementary for you if you have already done the complex geometry course, but I will do it in order to fix also our notations. Okay. So a complex manifold, X is a smooth manifold admitting a holomorphic structure, right? So a holomorphic atlas. Okay, so what is this? This is just well, maybe I will draw the picture here. So it's just a manifold, a smooth manifold that admits some charts. So here we have ui, phi I, to some open set in Cn. Okay, so this is a complex manifold of dimension n. Right. Phi j, uj. Doesn't matter. And here we have the intersection. And in the intersection, we have the change of variable map, which is just phi I composed with phi j. And this map is holomorphic. Okay, so in particular, this complex manifold is always smooth. It doesn't represent something with singularities. Okay. So this is a complex manifold, and so for every point, given any point, at every point, x in x, we can pick up a coordinate chart. If we choose a chart, let's say C1 to Cn, that goes from U contained in X to some B contained in Cn, right? Where U is a neighborhood of X, an open neighborhood. Then we can describe its tangent space at X, okay? So letting, if we write the coordinates Cj equal to xj plus I yj, then we can describe the tangent space at X. We can describe it, but I will use this notation, Tx(xr). That means that I'm taking the real tangent space. I mean, I'm looking X as a real manifold of dimension 2n, right? So this will be identified with the following vector space. It's just taking j equal 1 to n, and the reals times d over dxj plus the reals times d over dyj, right? We can identify it in this way, okay? So this is a real vector space of dimension 2n. Okay? Okay, so, well, we also have the tangent bundle, right? We have the real tangent bundle. On X. Right, that is, I will denote it in this way. Okay. And this is just, well, okay, I'm not explaining how do you construct this, the manifold structure on this manifold. Okay, you know it. Okay. Okay, so we can produce another vector bundle on X just by taking like the trivial bundle, the constant bundle C above X, and taking the tensor product with the real tangent bundle. So we have the complexified tangent bundle that is just TCX is TRX tensored with C, right? So at each fiber you're taking the tensor product with C, right? This means that this guy is just this vector space tensored with C, right? So in particular, this is a holomorphic vector bundle of rank 2n, okay, over X. Right, so it has at each fiber of this vector bundle is a complex vector space of dimension 2n. So it has real dimension 4n. You see? Okay. So, in particular, we have that this the complexified tangent space will be just the sum from j equal 1 to n of c times d over dxj plus c times d over dyj, right? And if we let, so now letting d over d cj to be 1 over 2 d over dxj minus I d over yj, dyj. I mean, this is like the analogous of the holomorphic derivation in one variable, you know. And we let the derivation respect to the conjugate variable as 1 over 2 d over dxj plus I d over dyj. And then we will have that this is exactly the sum from j equal 1 to n c times d over d cj plus c times d over d cj bar, right? Okay, so in particular, okay, so let's think a little bit about what are these derivations. I mean, so you know that the tangent space, the real tangent space, is just the space of derivations of germs of C-infinity functions to R, right? You can identify this real tangent space, this, where do I have it? These derivations with the space of derivations of germs of C-infinity functions defined in a neighborhood of X to R, right? So what happened when we complexify it? When we complexify it, what we will have is that these derivations correspond to, maybe I should write this. So these are R linear derivations of germs of C-infinity real functions defined in some neighborhood of X. So what will be these derivations? They will be C-linear derivations of what? Of C-infinity complex functions defined in some neighborhood of X in X. Okay, so, but what will happen? I mean, when I define these derivations, this d over dc and d over dc bar, you see that in particular when you restrict yourself to the to Cn, not to x, you see that a function f. So you will have that a function f. Let's say a germ of function from x to c, it's infinity, right? It will be is holomorphic at x if and only if all these partial derivatives are 0, right? Right? So in particular, I can identify this subspace of derivations, I mean the corresponding, for instance, to the d over dc bar, with the derivations that vanish on every holomorphic germ, right? And I also can identify these other derivations with the derivations that vanish on the anti-holomorphic germs of complex functions, right? So I have, and you know that this is independent of the choice of charts. This just is depending on the complex structure of X. Being holomorphic is something that doesn't depend on the chart that you're choosing. And being anti-holomorphic also, right? So in particular, I have a canonical decomposition, right? So we have a canonical decomposition of the complexified tangent space, right? As a sum of two parts, right? As tx10x plus t01xx, right? And this is the sum j equal 1 to n of c times d over d cj, and this is the sum from g equal 1 to n of c times d over d cj bar, right? And correspond to, these are derivations vanishing on holomorphic germs, no, anti-holomorphic germs, and these are the one vanishing on holomorphic germs. And you can show that this decomposition, in fact, comes from the composition of the complexified tangent bundle. So, in fact, we have two bundles here. So, in fact, we have that the complexified tangent bundle is a direct sum of two bundles over X. Okay, so we have two holomorphic bundles, each one of rank n above X. Okay, and this bundle can be identified with the holomorphic tangent bundle. I will denote it in this way. This is the holomorphic tangent bundle. And what do I mean by this? The holomorphic tangent bundle is the set, I mean, each tangent space of the holomorphic tangent bundle will be, it won't be exactly this. I mean, I'm here taking the space of derivations of complex valued infinity functions that vanish on anti-holomorphic germs, right? You can identify this with the set, with the space of germs of holomorphic functions, right? It's a germ of a holomorphic function, and it's kind of believable, right? I mean, you can think that this germ is kind of has an holomorphic and an anti-holomorphic part, but you're assuming that this anti-holomorphic part is always going to 0, so you can pass to the quotient, and you will get just like the holomorphic part. Okay. So this, in particular, I mean this Txx is the corresponds to a space of derivations of germs of holomorphic functions. Define it in some neighborhood. Okay, and this space, well, you should have seen it in a course of complex geometry, that it is just you can identify it with the Zariski tangent space. You know, it's the maximal ideal of x at x mod the maximal ideal of x at x squared is the dual of this space. Okay, where this maximal ideal is just the idea generated by the coordinates. Is where we're thinking that we are in a coordinate chart, and C1 to Cn are the charts in such a way that the 0 of this chart correspond to x inside the ring of holomorphic functions of Cn at x, well, of x at x, right? And this is just the quotient of the holomorphic functions of Cn mod the ones that vanish on x, right? Well, no, this is always no, this is Cn. I mean, this is just a smooth thing. So locally it is Cn. Okay. All right, we'll put it in this way. Okay. Okay, so now from all these vector bundles that we have over X, we can produce a lot of different sheaves, right, of sections of these things. So I will denote. Well, first of all, I will introduce the last one. That is the cotangent bundle. So we also have the complexified cotangent bundle. That is obtained from the complexified tangent bundle. I take it the dual as a complex vector space, right? Okay, so you have to be careful with all this stuff about being the dual as a complex vector space or as a real vector space. This is something that can be very confusing at some point. Okay. So what is this? At each point, the cotangent bundle, it will be just well, the sum of the duals of the holomorphic tangent bundle plus the anti-holomorphic tangent bundle, the dual of this, right? And we will denote these things in a chart in this way, right? J1 to n, C times dCj plus J1 to n, C times dCj bar. Okay, so this is the dual as a vector space. I mean, dCj over all these partial derivatives, I mean, over all these derivations, it will be 0, but it will be 1 just in d over dCj. Okay, and the same will happen with the other things. Okay, this is the dual as a complex vector space. Okay, and in particular, we can, if we have the the natural one forms that are the basis of the real cotangent bundle, we will see that dCj is exactly dxj plus I dyj, and dCj bar is dxj minus I dyj. Okay, this is an easy computation. Okay, so now let us introduce the sheaves, the forms. Okay, so first of all, I will denote it like this: omega 1 x infinity. Okay, this will be the sheaf of C infinity sections of the complexified cotangent bundle. Right, and this means that for every U open set in X, omega 1 x infinity of U is by definition the set of sections from U to TCX dual, such that S is C infinity and it is a section, right? Pi composed with S is equal to the identity of U. Right? So how do these guys look like when we choose a chart? So if U, let's say C1 to Cn, from U to Cn is a chart, then we can identify a section. Well, I won't use this letter. This is a bad letter. Omega, right? Omega for a differential form. Okay, so using this chart, we can identify omega. Omega will be written, I mean, if we put it a name here, then phi star omega. It will be something like this. It will be a sum of fj dcj plus gj dcj bar from j equal 1 to n, where this fj and gj are functions from U to C, which are of C infinity functions. Okay? This is this sheaf. In particular, this sheaf admit, I mean, this is like, well, these are the functions. I mean, they are C infinity. Locally, they are dc bar times C infinity functions. Okay? Okay, so this sheaf, we know that it has a decomposition, right? I mean, it's obvious, in fact, from this, right? It's omega 1 x infinity has a decomposition as a sum of two sheaves, 1 0 x infinity plus 0 1 x infinity, right? And well, you know what all these guys mean. I mean, this is the sections, C infinity sections of the holomorphic tangent bundle, and these are C infinity sections of the anti-holomorphic tangent bundle. Okay, and locally you will see that they are just written in this way, and the other in this way, a sum of these things. If you want what? Yeah, duals. Thanks. Right, yes. Okay, so we have these sheaves that are like infinity modules, right? And we will denote. So we will say, we say that a section omega in omega 1x infinity of U is holomorphic. So it's a holomorphic one form if you can write it as whenever you write it locally. So if you start of omega, it's the sum of fj dcj j equal 1 to n, where this fj now from U to C are holomorphic. Right? So in particular, we have a subsheaf of the sheaf of 1-0 forms. That is the sheaf of holomorphic forms, and we will denote it like this. So this is omega 1 x n, okay, of analytic. Okay, so this is the sheaf of holomorphic sections, holomorphic one forms, right? And this is the same of the sheaf of holomorphic sections of the holomorphic cotangent bundle Tx dual, right? And this is a subsheaf of omega 1, 0, x infinity. Okay? Clear? Okay, so this is the first sheaf that I have introduced just in the category of holomorphic things, right? Holomorphic functions and manifolds. Okay, what else? Well, now we can take the wedge products, right? Taking the exterior products. We will get so wedge K of the complexified cotangent bundle. It will have a natural decomposition as a sum P plus Q equal to K of the wedge P of the holomorphic cotangent bundle tensored with the wedge Q of the anti-holomorphic cotangent bundle, right? Right? And so we can define the sheaves of sections, of C-infinity sections of each of these bundles. And we get, so we define omega k x infinity. We define it as the C-infinity sections of this bundle, right? And we will have that this is has a natural decomposition of sheaves which correspond to the omega pq x infinity that are just the C infinity sections of this bundle here, right? And so again, locally, how will a K form look like? So omega in omega k x infinity of u for some chart, right? We will look at it as it will look like a sum of, let's say, okay, this I'm trying to do this in order not to confuse you, but maybe it will be a little bit confusing. So well, let's see. 1 less or equal than I1 less than IP less or equal than N, J bigger or equal than 1 and less than JQ less or equal than N, and P plus Q equal to K. I don't know if you can see this. And here we have a function f depending on all these indexes. So I will write it just like ij, where I is the multi-index I1 to IP, and j is j1 to jq, times dc I1 wedge blah 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 dc IP wedge dc j1 bar wedge dc jq bar. Okay, so you see that here I'm mixing the amount of holomorphic forms that appear and the amount of anti-holomorphic forms. I am mixing the amount. I mean, it can appear here one part corresponding only to holomorphic forms. You see, a known anti-holomorphic form here. And maybe there is another part that just with one anti-holomorphic form, and so on, with two, and it has all the possibilities here, right? But an element of this sheaf will only have a fixed amount of holomorphic forms and anti-holomorphic forms. That it will be P holomorphic forms and Q anti-holomorphic forms. So I won't write this again, you see. I mean, I won't write how does an element of these sheaves looks like, because it's exactly the same thing, but fixing P and Q. Okay? So it's not confusing, it's clear. Okay. And these guys are infinity functions, right? Okay, well, and we call these elements. So the sheaf, we call them. This is the sheaf of PQ forms. Okay, this is what I mean by a PQ form. Okay. What else? Okay. Now, well, you know that in the real case we have this exterior derivative, right? So in the complexified case, we define it in this very same way, right? So we have an exterior derivative d goes from the sheaf of infinity k forms to k plus 1 forms, right? This is a morphism of sheaves, and it's defined in the same way that you define it in the real case, right? So it's just so if you have, so locally, if you have an omega that can be written in this way, fi j of, I will write it in this way for short, dci wedge dc bar j. You understand the notation, right? So I and j are subsets of 1 to n, and the cardinality is k. So if you have this form locally, the derivative of this will be just, by definition, the sum of the same thing, d fij wedge dci wedge dc bar j. And what is this? I mean, for k equal to 0, I have to define it, and it's just this is just, so the partial derivative of fij with respect to will be the sum from j equal to 1 up to n, partial derivative with respect to cj times dcj plus the partial derivative with respect to cj bar times dcj bar. Okay, the same thing as in the real case. And this is well defined, this is independent of the choice of charts, and blah, blah, blah. Okay? And we also have that this is a complex, right? So it's the same account that you do in the real case, shows that we have that d composed with d is 0. Okay, so we have a complex. We have the de Rham complex. Okay, that is just, well, I will start it from here, 0, omega 0 x infinity, omega 1 x infinity, d, and so on, right? Okay, so in particular, when we take global sections, let's say the de Rham complex of sheaves, I don't know. Okay, so when we take global sections of these sheaves, we will have a complex of abelian groups, right? I mean, of vector spaces. So in particular, we have this complex. And from here, we can define the Rham cohomology, right? So we define the Rham cohomology groups. So we have Rham cohomology groups, and we denote it like this. HKdR of x is by definition the kth homology group of this complex, right? Omega dot x infinity of x, the global sections of this, relative to the differential map D. Okay? And this is nothing else than the real Rham cohomology, the usual one, tensored with C. Okay, it's like the Rham cohomology with complex coefficients. Okay, it's a complex vector space. Good. Okay, so let's look at this differential, exterior differential, in this decomposition of the sheaf of K forms. So when we restrict it, when we restrict D to one of these sheaves of PQ forms, we have a map D from the sheaf of PQ forms to, well, it also goes to P plus Q plus 1 forms, but not to all PQ plus Q plus 1 forms. It goes to P plus 1 Q forms plus PQ plus 1 forms. Right, and this, you can see this just by looking at this formula, right? Here you have P holomorphic 1 forms, Q anti-holomorphic 1 forms, and when you derive this F, it will appear just one holomorphic and one anti-holomorphic form. So when you do the wedge product here, this will grow up by 1, and this will grow up by 1. You know, so you will end up in this situation, and you can look at this. I don't know how to do this in order to, so maybe it should do this. I should do this like this: omega pq x infinity. Here I have d that goes to omega p plus 1 q x infinity, pq plus 1 x infinity, and here I have the projections, p plus 1 q, the other projection, pq plus 1 x infinity, and I have these composition maps, and these maps we will call them just delta and delta bar. Okay, that is the holomorphic exterior differential and the anti-holomorphic exterior differential. And the formula of these guys is clear here. I mean, you just have to take this form, and the holomorphic differential will derivate this only with respect to the holomorphic coordinates, and the anti-holomorphic one will derivate it only with respect to the anti-holomorphic coordinates. Right, and in particular we have this, right? D is equal to delta plus delta bar, right? And so this relation D equal to 0 is now decomposed in 3 different relations. The first relation is that delta O delta is 0. The other relation is that delta O delta bar is equal to minus delta bar O delta, and delta bar O delta bar is also 0. Right? This is the same thing, and this is obvious just because we have here direct sums, right? It's just that. This is the same as this. And so in particular we have another complex. We have another complex that is called the Dolbeault complex. Here of sheaves. Okay, and what is this complex? Just here, omega p0 x infinity delta bar omega p1 x infinity delta bar omega p2 x infinity, and so on. Right? So again, we can take global sections of this complex. We will get another complex of vector spaces, complex vector spaces, and we can define the Dolbeault cohomology, right? Okay, and these are also complex vector spaces. So these are denoted like this: HPQ delta bar of X is by definition the HQ, the Q homology group of the complex omega p dot x infinity of X with respect to the partial bar. Okay. Okay. So in particular, these groups, this group are analytic or holomorphic invariants. Right? These are invariants of the analytic structure of X. I mean, just having a infinity diffeomorphism between X and other complex manifold won't give you an isomorphism of Dolbeault groups, as it will give you in the case of the Rham cohomology. Right? I mean, this is a infinity invariant. Okay. Well, in fact, it's more than infinity. It's continuous. It's homotopic invariant. Okay. Okay. So we have these groups. So, do you have any questions? No. What else? What time is it? Almost 6. Okay. Cool. So now I will introduce some metrics on complex manifold, and well, later in the next lectures we will see how these the properties of these metrics can be used in order to have a better understanding of the relationship between these two groups, the Rham cohomology and the Dolbeault groups, Dolbeault cohomology groups. Okay, this is essentially the Hodge decomposition theorem. That it's a very long result. It's hard to prove, and we will spend like maybe 3 or 4 classes just trying to get there. Okay. Okay. So now. Definition. So let E X be a holomorphic vector bundle any holomorphic vector bundle, okay, over a complex manifold. Okay, so a Hermitian metric on E is a section, a global section, global holomorphic section holomorphic, no, it's infinity. It's infinity. It's infinity section of the following vector bundle. It's E tensor with E bar dual, right? So what does this mean? I mean, Hermitian metric, let's say H on E. So what does this mean? This means that at each point of X, I am what's the word? I am associating a pairing on E that is a Hermitian pairing. Okay, so and it's depending on x, it is depending smoothly on x, okay, in a infinity way. Okay, so for every i.e. for every x in x, I have some map hx that goes from e times e to c, right? That is c linear in the first coordinate and c antilinear in the second coordinate, right? I don't know what's, maybe there's another word, skew linear? No? Well, I don't. Okay, so we have these relations. It's hx of ub is equal to hx of bu bar for every ub in E and for every x in x. So, well, here I am adding the assumptions that it is Hermitian, right? So I want to have this condition, and I also want to have so here such that I also want to have this other property that hx of uu is bigger than 0 for every u in E minus 0. I mean, no, this is not, this is ex, 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 and for every x in x. Right? It's non-degenerate. Okay? So this is what it is, an Hermitian metric on a holomorphic vector bundle. So a Hermitian manifold is a complex manifold X with a Hermitian matrix, Hermitian matrix on its holomorphic tangent bundle, Tx, T10x. Right? Okay, so in coordinates, so locally in coordinates, we can always write H in the following way. H, it will be exactly a sum from j equal to 1, ij 1 to n, hij times dci tensor with dcj bar. Okay, where these functions are infinity functions, hij, I mean this matrix are infinity depending on x, right? On the variable x in x, and they are Hermitian, right? Hermitian matrix. Is this correct? Okay. Okay, and what do I mean by Hermitian is just this, right? H ij bar is equal to hji. Well, and the other property that the matrix is positive, right? Okay. This Okay, so in particular, every Hermitian matrix, well, every Hermitian manifold has an associated 1-1 form. We can identify, well, by definition, let's say, the associated one-1 form on XH is by definition. So by definition, this omega, there is minus it's I over 2 H minus H bar. There is minus the imaginary part of H. And this is just in local coordinates. So it's I over 2, the sum ij equal 1 to n of hij dci times dcj bar minus dcj bar times dci. Right? I mean, here I'm using the properties of hij being Hermitian. Okay. And well, this you can see this. You can think of it as a 1-1 form if you're thinking forms as alternating bilinear maps from the cotangent bundle, and you have here to identify like the DC bar with the bar of DC. And so, well, so in fact the one form will be in fact omega equal to I over 2, the sum ij equal 1 to n hij dci wedge dcj bar. Right? This is the identification that you're doing. This is this by definition. Okay? So this is the one-word form associated to Hermitian manifold, and okay, and definition. Maybe here we say that XH is Kähler. Well, and you see that you can recover H from omega, right? I mean, having H or having omega is the same thing, right? So maybe I will write it like this. When I write it X omega, I am talking about the 1-1 form. I write it XH, I'm talking about the Hermitian matrix. Okay. Maybe it's Kähler if H is a Kähler metric and this means so maybe, well, in this way, this is Kähler if this is a Kähler metric, and this means that the associated 1-1 form omega is closed, right? And this means d omega is 0. Is d closed, okay? D omega is partial plus bar partial bar, okay? So this is the definition of a Kähler manifold. Okay, so an example of Kähler manifold, well, our main example, in fact, is the projective space. Okay, so example. The projective space Pn is a Kähler manifold with the following metric that is called the Fubini-Study metric. Okay, what is Fubini-Study? Well, I won't write the metric, I will write the one form associated to it. So it's just I over 2 pi times, here you have z0, well, I will have, the coordinates here will be c0 up to cn. So it's c0 bar plus cn bar times c0, I mean dc0, which dc0 bar plus dcn, which dcn bar, minus, here you have c0 bar, or the other direction than this, c0 bar dc0 until cn bar dcn, which c0 dc0 bar plus cn dcn bar, and all this over c0 bar plus cn bar squared. Okay, so this is Fubini-Study. Well, you have to do the count to check that this is closed, and to check that it is Hermitian metric. It's also it's easy. I mean, this metric comes from the affine space, right? It's just taking the, you can obtain it. You obtain it from the natural metric, the canonical Hermitian metric on C n plus 1, but you are identifying, you're using the following map, right, via the map that takes C0 to Cn to C0 over the norm of Z, Cn over the norm of Z, right? So you're normalizing. Well, this is the norm squared, the norm to the 4, okay? And obviously the Hermitian matrix here is Kähler, right? Okay, and well, this number 1 over pi, it will be explained later. I will explain it in a few moments. Well, I will explain why it appears later. Okay, and in particular, if we have a Kähler metric on the projective space, so every smooth projective variety is Kähler. Okay, with the Fubini-Study metric restricted to the subvariety, right? It will be still closed, it will be still Hermitian, right? Okay, so this is good. What else? Okay, now I want to recall, I don't know what time is it. Okay, so we still have time. So I want to recall remark. So you don't have questions, no? You believe this just by faith? Okay. Okay, so I mean let X be a compact complex manifold of dimension n. Okay, and let delta be any element of the homology. So if I have here delta in hk of x, remember that whenever I don't put the coefficients, I'm talking about the integers. Okay? Well, when I'm talking about singular homology, when I'm talking about de Rham cohomology, the coefficients that are missing are the complex numbers. Okay. Okay, so if I have any delta here, you know that this guy induces by Poincaré duality. It induces an element here, right, in the dual, right, the home of h2n minus kx to z, right? Okay, but it also induces an element on the, I mean, well, there is another theorem that relates the home of, I mean, like the dual of a homology group with the de Rham cohomology, right? So I will recall this theorem. I won't prove it. I will just assume it, that you have already seen this before. So recall this theorem. This is de Rham isomorphism. Okay, and it says that so let X be a smooth manifold right. Then we have the following isomorphism, the map. So here I will take K, the Rham cohomology of X. So let's take omega here, goes to the following map that takes some mu in hk of x with complex coefficients. Here I'm talking about the singular homology with complex coefficients to the map, integration map. This goes to C. So this is an element of hkxc dual, right? This map is an isomorphism. Right? Okay, so this is the Rham isomorphism. So using the Rham isomorphism, so we know that this delta in hk, in fact, is inducing an element here, right? Some element in home of H2n minus kx z tensor with C, right? And this is just the home of H2n minus kx. Here I'm using the universal coefficient theorem. I will just write it like this. Right? And so we know that there exists a unique omega in H2n minus k de Rham such that so what's happening? Delta times mu is equal to the integral of omega over mu for every mu in H2n minus k x with complex coefficients. Right? So each element of the homology induces a unique element in the de Rham cohomology, and I will call it, I will denote it like this, delta PD, like Poincaré dual. Okay?
Just one question. Delta is in HK of x with integer coefficients?
Integer coefficients. Yeah. Well, it doesn't matter. It could be in complex coefficients also. It doesn't. I mean, if I have one with integer coefficients, it will induce this delta PD, but you don't have a correspondence, right? You can have something that is non-zero here and goes to 0 here, right? I'm not saying that you have the correspondence. I'm just saying that in this direction you have the function well defined. Okay. Okay, so, and also you can do the same thing if you start with delta, an element of the singular homology with rational coefficients, right? Or with any coefficients that you can do then the tensor product with Z, right? Anything that is inside C, right? Okay, and so the definition is here. So we say in this context that omega in H2n minus k de Rham x is an integral class and here I will say respectively rational class if it comes from something in the homology with integer coefficients or with rational coefficients, right? So if omega is equal to delta PD for some delta in HKX, right? And here respectively delta in HKX with rational coefficients. Okay. So, well, we will. Now I will explain why did I put this 1 over pi here, and it's just in order to make the Fubini-Study matrix an integral class. Okay. So here I will put the example. The Fubini-Study matrix is an integral class. Okay, in fact, what we will see is that omega fs is the Poincaré dual of Pn minus 1 Pd, right? And what do I mean by this? I mean that this is the homological class of the linear subvariety of codimension 1 in Pn, right? In fact, this is true. Okay, so why is this true? So in order to see this, note that since we already know that h2n minus 2 of Pn is the integers times this class, right? So in particular, we know that I didn't mention that before, but if we restrict ourselves here to delta being in the homology group with complex coefficients, then this correspondence this will be a correspondence, you know. This will be bijective when we restrict ourselves to the singular homology with complex coefficients, right? So we already know that this omega fs is equal to the Poincaré dual of something. I mean, it's delta Pd for some delta in h2n minus 2 of Pn with complex coefficients, right? And this is exactly the same thing as C times Pn minus 1, right? In particular, we know that omega fs is some alpha times this for some alpha complex number. And what is this alpha? How can I compute this alpha? So I will compute it. I mean, alpha is so if alpha is obviously equal to alpha times Pn minus 1 times P1, right? It's the intersection of this cycle times P1, right? And this is just by Poincaré duality. I know that this guy is the Poincaré dual of this guy is omega fs, right? So this will be just the integral over P1 of omega fs. So I just need to compute this integral. And now I can choose P1. I mean, let's take P1 as x2 equal to x3 equal to xn equal to 0. Okay, so it just depends on two variables, x0 and x1, right? And let us restrict ourselves to, so restrict omega fs to the affine part of this P1. This will be P1 minus the point 0, 1, 0, 0, okay? And let's identify this with C, okay? So I am just taking x1 as the variable, and x0 is going downstairs, okay? So I'm removing everything here. Okay, yeah, I use x and, well, let's say z. Right? I'm removing all these variables, and I am taking the variable, I'm taking out x0 equal to 0, so, I mean z0 equal to 0, so I'm taking z0 equal to 1. Right? So what I will get is the following integral. So alpha will be equal to the following thing. So it's the integral over c of I over 2 pi of dz wedge dc bar over 1 plus mod of z squared squared. No, not squared. Just like this. Right? No, this is squared. That's correct. I think so. Okay. So I will compute this. Well, you just need to do this change of variables things. You can write it in real coordinates, so you will have the integral of on R2 of 1 over 2 pi dx wedge dy over 1 plus x squared plus y squared squared, and then you will use this change of variables, the standard change of variables polar coordinates, and you will get that this is 1 over 2 pi. The integral, no, this is not 2 pi, it's pi. The integral from 0 to infinity, 0 to 2 pi, r dr d theta over 1 plus r squared squared, and then you will get that this is the primitive of minus 1 over 1 plus, let's say, r squared between 0 and infinity, and this is just 1. Okay, so this is why we put this pi. I mean, we're normalizing it in order to make it an integral class. Okay, and so what time is it? Okay, well, in the last minutes I will just state a theorem that I won't prove in this course. This is a theorem that is usually proved in the complex geometry course. That is the Kodaira embedding theorem. Well, this is a version of Kodaira embedding, right? So let X be a compact complex manifold okay. How do I state this? Then there exists a projective embedding X into some Pn phi if and only if X admits a Kähler metric with associated one form form omega, such that omega is integral, is an integral class. Omega is an integral class here in H2. The Rham of X is an integral class. This is well defined. I mean, since the Kähler is, since the metric is Kähler, omega would be closed. So it will represent an element is in the de Rham cohomology. So this makes sense. Okay, and furthermore, in such case, we can choose omega, or we can choose phi. I mean, we may have, let's say that omega is equal to phi star of the Fubini-Study metric on Pn. It's the pullback of the Fubini-Study metric. Okay, so with this theorem, we're characterizing the Kähler manifolds that are projective. Okay, it's just up to know whether if this one form is integral or not. Okay, so in particular, whenever you have a rational class here, you will also have some metric where you can project X in subprojective space. So it will be projective also, if you're thinking in being projective as something abstract. Okay. Well, that's. Do you have any questions?
Could you repeat the last argument, please?
The last part of what? The state.
What happens with the class of omega is rational, for example?
If it's rational, you know that some multiple of it will be integral, right? So in particular, a multiple of it will correspond to some projective embedding, right? So in particular, it will exist some projective embedding. I mean, it's not true that every compact complex manifold is projective. That's not true. I mean, the thing that happens in the real case doesn't happen in the complex case. And we will see some counterexamples of that. I mean, for instance, a criterion for proving that some compact complex manifold is not projective is the Hodge decomposition. I mean, we will prove that every Kähler compact Kähler manifold, well, it will satisfy the Hodge. No, well, yeah. Every compact Kähler manifold will satisfy the Hodge decomposition, right? So maybe there are some compact complex manifold that are not even Kähler, you know, but because they won't satisfy the Hodge decomposition. And it will be trivial to produce these guys because are some very simple linear algebra things. I mean, it's so if they are not Kähler, they are not obviously projective, right? So not every compact complex manifold is projective, right? So I'm just saying that having a rational class in H2 implies that it is projective, right?